Hello everyone, I'm Jorge Zepeda O, creator of the Knowing Nothing Outside of Tracking, or NOT algorithm, and I'm here today to show you how to download and run NOT with the provided sample data. First things first, we want to go to our GitHub page at https://github.com/landaslab/NOT and download the source code. Once downloaded, access your downloads folder and you'll see the zip file here. Extract the zip file to your downloads folder and open it up. Now, NOT requires Python 3.5 or higher and plenty of scientific packages to run properly, so we will quickly install the Anaconda framework to handle most of that for us. Get the individual edition for now. Here, we can find it at https://www.anaconda.com/products/individual-d. The download should be present here for your specific OS. Once we've downloaded it, which we already have, run the installer and follow the on-screen instructions to complete the setup. For example, here we will click Next, agree to the license agreement, install for just you, select your destination folder, let Anaconda pick its default settings for the advanced installation options. We have already installed Anaconda, but you will need to press the install button. Once Anaconda is installed, we can close our internet and our downloads folder for now and open up the Anaconda Navigator. You can find it in the Start menu under Anaconda 3. Now we will select the Environments tab, and we can check that we have the following packages installed. Ideally, the base environment, unless you want to specifically install another environment. Now, go to the All, and then search the following. NumPy, check that it's installed. Image.io, also installed. SciPy, check. Matplotlib, check. And PyFFTW, check. Now, odds are you won't be able to install the PyFFTW package, so we will need to open up the Anaconda prompt with administrator privileges. Minimize Anaconda Navigator for now. Go to your Start menu, Anaconda 3, Anaconda prompt, and right-click it to run it with administrator privileges. If you're not an administrator on your computer, ask the administrator to install this for you. Now, to install PyFFTW for the fastest Fourier transform in the West, we want to type in the following command: conda install -c conda-forge PyFFTW, and then press enter. Anaconda will be searching for the environments, and as you can see, we've already installed the most recent PyFFTW package. Now you can close Anaconda prompt and return to the Home tab in Anaconda Navigator. Pick your favorite IDE and click either Launch or Install. Here, we will be using VS Code for its functionality not only in Python, but in other languages as well. If you prefer a different IDE, make sure that you take the appropriate steps to set Python up in that environment. Here we will launch Visual Studio Code, and by default, VS Code will not be able to run Python, so we'll need to open up the marketplace to download the Python for VS Code extension. You can find it here. Search Python and install the one by Microsoft. You may additionally want a few other extensions, for example the Anaconda extension, but it's not necessary for here. Once that's been installed, we can then open up the folder where NOT is located in VS Code. Here we should see the several folders inside. That's how we know we're at the right spot. We select that folder. We will have access to all of the files that NOT contains. Select the main.py file and you will see the following screen. Once we've seen this screen, we would like to be able to see everything that Not's doing for this particular run. So let's set the visual values to true. Now, we will only evaluate the first image here, test_beads, for this demonstration. So type test_beads in the codes list. Now, press run, or F5, to begin. Five figures will appear, and Not will pause execution briefly. 1, 2, 3, 4, 5. The contents of figure 1 is the first frame of the image file selected, while the other 4 figures are samples of the double helix point spread function kernel used. You can use these to ensure that the phase mask approximately fits the point spread function observed. For example, we can scooch this closer to the side and see that they compare very well with what we see experimentally. When satisfied, we can close these 5 figures, and then Not will pre-process the image and the kernel and send more figures your way. Let us look at figure 1 once again. This here is the pre-processed image with background subtraction and noise suppression. Figures 2 through 6 are samples of the pre-processed phase mask. There shouldn't be much difference between these and the samples we've previously seen. Nonetheless, this is your last chance to make sure that the PSF aligns before deconvolution. Figure 7 contains the local variance of the data. Because the background intensity here is consistent, the local variance appears mostly around where the emitters themselves are. So finally, figure 8 is the image after local thresholding using the local variance. This is basically what ADMM sees during deconvolution. We can close the figures and let Not continue. Now this next figure here will stay in place, very cloudy, until a few pixels will start turning white. This is the deconvolution image of Not, with intensity on a log scale. Once Not has finished iterating through a single frame, the image will stop updating and you can close the figure. Here we can see that several dots are appearing. Each one of these corresponds to a high confidence that this is a particle. Now the image has stopped updating, so we can close the figure. Now 2 more figures will appear, one in 3D and one in 2D. Looking at the 3D figure, we can see where ADMM has determined particles are and about how confident it is that they are in fact particles. A larger sphere, such as these, indicates a higher confidence. Now the 2D images show the input image on the left, the deconvolution image we saw earlier in the middle, but no longer with the logarithm axis, and the locations of the potential particles in 2D on the right. You may note that some of the double helix point spread functions were either not captured, and some lobes have multiple localizations. The multiple localizations are due to the fact that one lobe is more intense than the other, and the best way for ADMM to represent that without compromising the reconstructed image is to attribute many low confidence localizations to that lobe in a circle. In extreme cases, this will become apparent, and it is a difficult problem to fix. A fix, however, is in the works, and the GitHub will be updated when it is complete. The missing localizations, on the other hand, are due to those PSFs being below the local threshold. We can incorporate low-intensity emitters like this, and I'll show you how to in just a moment, but be warned that in doing so may cause noise to be considered as particles. Now, it will proceed to the next frame and repeat the same process. So, when satisfied, you can close those 2 figures and let the deconvolution image for the next frame appear. If you'd like, you can watch this each time, but that won't be very efficient and should only be used for debugging purposes. Let us stop execution for now and change 3 of these values in the visual dictionary on line 18. Let us set the initialization, INI, the preprocessing, PRE, and the recovery, REC, to false. This will prevent figures from appearing. When handling multiple files, this will become incredibly useful, as ideally you don't want Python to stop multiple times during each file, so it's common that actually the visual dictionary is full of false values. We will continue this going on forward. Now, while we're here, let's take note of the update dictionary just one line above. Not saves its progress 5 times for each analysis, once at the end of each step. Setting these values to true will cause not to redo that task with the loaded data from the previous. Else, setting the value to false will cause not to skip over that step of the analysis and focus on the subsequent tasks, using data previously saved. If there is no data and the update values are set to false, not will proceed as if they were set to true. I advise to have INI, pre, and rec set to true while you're determining preprocessing and deconvolution parameters, and set them to false when you determine particle identification and tracking parameters. Now, let's run not for real. As you can see, no figures have appeared, meaning that the process will not be interrupted. Now, depending on the size of the movie you're processing, this may take a while, so feel free to get several data sets in the lab and let it run overnight or over the weekend. Once Knot finishes, you'll find 5 files for that image in the Knot's temp folder under image name. Knot, temp, image name. We have 5 different files. From left to right, the files are the segmented point clouds, the local variance for each frame, the preprocessed phase mask kernel, the preprocessed image, and all of the points found during deconvolution. We can back out to the MATLAB folder, which we can find a .mat file with the file name on it that contains the trajectory information in a manner similar to the previous work in the Landes lab, notably Troika. Similarly, we can, in the evaluation folder, there is an XML file for each dataset with the particle trajectories organized slightly differently. These files are used by Knot, or you, to jump into the middle of analysis or to do some post-processing on the data observed. Okay, this is taking a bit long. As we can see, it'll probably finish at about 35 minutes. And chances are, when you're getting data from your camera, it will be very large. We're talking about 1,000 frames of about 512 by 512 images. The one we're analyzing right now is 50 frames of 256 by 256. So, Knot won't be able to handle such large data sets in a reasonable amount of time. It will handle them, but just not quickly. However, do not fear, as we can crop to the region of interest of a dataset with Knot to analyze. So, let's learn how to crop images with Knot, and copy the testbeads.tiff file into the experiment folder, which you may have to create. Now, go back to VS Code and open the crop.py file. You will be greeted by a slightly less friendly set of code that we will need to modify. To make sure we're doing everything right, let's actually open up the image in ImageJ, or Fiji, or your favorite .tiff file viewer. Now, zooming in and adjusting the brightness and contrast appropriately, we can see that, there's some interesting behavior up in the top left. So, in this top left quadrant, up here, for like the first 20 frames, we want to capture that behavior. So we can go back to VS Code and modify the crop.py file to select the region of interest that we're looking for. Now, let's modify the frames parameter from 0 to 20, the ROI sen parameter, or that is the center of the region of interest, to 64 by 64, and the ROI size to 128 by 128. I will make a note here and say that it's best to keep the ROI size a square, and ideally a power of 2 or another highly composite number like 96 or 120 for best performance. Then make sure that the files list down here is the file that we're actually looking for. So test beads.tiff, and we're all set. We can now run the crop.py, and it will present us with another figure. Now it will show us the region of interest that we've selected inside this red box on both the first frame and the last frame. And not won't do anything until we have closed this figure. If you don't want this region, halt the process, stop it, and we can try a different spot. However, we do want this figure, so we'll close it. Note that because we have files as a list, it is possible to do multiple files at once, but only with the same region of interest. Now, if we go back to our images folder, we will see that the ROI that we've cropped. Let's take that file name. You can press F2 to grab that. Go back to main.py and paste it into the codes list, or rename it as you see fit, and let's rerun not. Here we'll see that the file name actually contains the information about where the ROI was taken, in case you forget or you want to take multiple ROIs of the same movie. Oh wow, that is going much faster. Indeed. It looks like Not should finish in about 3 minutes, which is much more manageable. And that, folks, is how you crop an image using Not. After waiting for a bit, our Not analysis is finished, and we can now actually set update to false. So we don't have to do it again. And set the last visual value to true. This will show us the trajectories that Not has found. Running it again, we'll see that Not passes by everything else and shows us beautiful trajectories in 3D and in 2D. The color gradient that you see here is actually representing the time axis, going from light to dark as time moves forward. Now, it's up to you, dear researcher, to analyze this and draw whatever important conclusions you have from this data. But don't leave just yet. There's one more very important file that we should look into real quickly. The user.py. Now, this is the entire list of user-defined parameters for Not. It is broken up into 3 main sections: instrument, simulation, and processing. Put simply, once you've set the instrument parameters, you won't need to change them for as long as you use the same instrument. The simulation parameters are really only used when simulating test images with Not, which will be a subsequent video. And the processing parameters should also only need to be set once when you match the simulated PSF to the experimental PSF. Do note that sometimes varying some parameters, such as pre-EPS or rec-iter, may give you better results in specific use cases. Similarly, in tracking, track radius, track len, and track min may come in handy if you need to have a larger search radius, longer sliding window, or just want to remove short trajectories, respectively. Additional parameters are briefly described in the associated comments. And that's all for this introductory guide to Not. More advanced topics are discussed in the user guide in the GitHub, but don't be afraid to experiment and adapt Not for your own purposes. All I ask is that you cite us in your next big breakthrough. Until then, happy tracking.